It's like instead of a cape, it's an umbrella.
Exactly. Exactly. Yeah. This is good. This is good to remember. Okay.
All right,
our superheroes now come with umbrellas. Okay.
Yeah,
well, this was helpful. Exactly. There you go. There you go. Hi, everyone, and welcome back to SandboxAQ's podcast, fAQ. I am Tai-Danae, and I am joined by Adam again, and we're here to chat about all things in the intersection of artificial intelligence and quantum, including applications, but also concepts. Now, last time, Adam, in our previous episode, we were focusing on a really fundamental piece of quantum physics and quantum technologies called qubit, which, just to give folks kind of a refresher, is essentially a basic unit of information in the quantum world. Now, when we were talking about qubits and what are they sort of conceptually, and then also how are they used in applications, we kind of left off a really fundamental part of what makes qubits qubits. But we're here to talk about that today. And so maybe I'll just kind of give away the punchline up front. That word is a concept called superposition. That's the concept that we're going to focus on in today's episode. So Adam, let me just throw this out there to you. What superposition?
Oh yeah, sure. Like just cover that in a sentence or two, and then we'll just be done, right?
We're done.
That's the hope for today.
Exactly.
Yeah, it's a strange concept. It was strange for me, at least. I think that as I've learned more, it's less strange. But I already feel like I'm walking around this issue and not actually answering your question. I'm just saying it's weird, but it's not weird. And it used to be weird and it feels less weird now. But notice I'm not saying what it is at all.
Right.
Because it's still it feels like a tricky concept to be able to explain. And I think I'll hedge even more by saying before we get into what it is and try to kind of concretely describe and define what it is. Let's talk about the word, because I think this is one of the first words that I ever heard about when I first started learning about quantum mechanics and quantum applications, quantum technology, all the quantum things. And at first it felt very mysterious and super because it's got the word super in it. So I was kind of thinking superposition, this amazing, different, magical thing that's got a cape on it or something.
Yeah.
So I don't know. Let's break it down a little bit into the best that we can to the sort of the etymology or the history of that word. Does that feel like an okay place to
Definitely.
start?
Yeah, I think that's a great place to start, because I don't think that superposition is a word that most human beings use in their everyday conversations. So I think breaking it down is a good way to start. So I think you've done a little bit of research in this. Maybe you can tell us a little bit about kind of what the word means from a, etymological perspective.
Sure. Yeah. And I'll do some reading here. Just, I don't have all this memorized. So the best that I could find is that it's a very old word. So definitely predates quantum physics back in the mid 1600s. From the French, which was derived from the Latin, which means a placing over. So it's a noun of action from past participle stem of superponere, to place over, from super plus ponere, to put or to place. So basically putting something above something else. So a position above other positions. Is the root meaning of the word, as best as I can tell. And I know you mentioned before that most humans probably haven't heard of the word superposition. Some of my geologist friends have. Back in another life, I used to create content for middle school science, and I remember creating an exercise looking at different strata in the Earth's crust. So when you're digging for dinosaur bones or something, there's layers of different types of soil or rock on top of another. And there's always the principle. There was a principle talked about, the principle of superposition in geology, meaning that layers that are on top or in superposition to other layers are younger than the layers that are lower. So that's the first time that I had heard of superposition before getting into the quantum realm. But that just really honestly kind of confused me more. like at the moment when I first started learning about it in the physics context. But it sounds like, was this the first time that you had heard of the word superposition was in a physics or a quantum context? Is that right?
Well, okay. The interesting thing, so I love the analogy that you just gave, or I guess it's not an analogy, it's a fact. I love that. I think it's very clarifying, actually. All of these synapses are now going off in my brain. To answer your question, so superposition is a concept that is used in quantum physics. But as you just said, the same concept can arise in other fields, other domains in science, and also mathematics. So I actually learned the math behind superposition before I learned that physicists call that thing superposition. So kind of like you, I learned the idea and then later learned, oh, another field in science calls that idea by a different name. So for me, I learned about the kind of concept first, and then later on I was like, oh, why are these other folks calling it something else? And then also, why does it now feel weirder and spookier than it did, like in your case when you're like studying different strata and the Earth's crust, and then for me when I was talking about math things. So that just could, and maybe we'll get to this later, like why does it feel potentially counterintuitive or whatever it is? We haven't even really said what it is in quantum physics. Why does it feel weird to some folks or in the popular media when the concept is actually something that we could come across in day-to-day lives if you're a geologist, for example?
Yeah. Yeah, no, it's a good point. And I think for me in the geology context, and maybe for you in the mathematical context, superposition just feels very normal and easy to explain.
Yeah.
Like if you're looking at different cut, like doing a cut of rock and you see these different layers, one is in the superposition to others. Great. Makes a lot of sense. When we start talking about it in the physics sense, all of a sudden things seem to get fuzzier when we're talking about, well, if something's in a superposition, it's in a combination of two positions and you can't really know what position it's actually in unless you measure it, and then it collapses and things get like they feel very mysterious because the meaning is a little bit different because you're trying to describe something in nature that has this property called superposition, which essentially means that it's in a combination of different states, or it's in a combination of different positions. At least that's my sort of initial understanding, but I think you know a little bit more about this than I do, and maybe you can talk for a little bit about what superposition means to you, and then maybe we can kind of come to some kind of agreement together.
Yeah, I think that's a good idea. So just for the record, so that it's super clear to the audience, we will now state what superposition is. So we've been dancing around it for a few minutes, but now, maybe let's say explicitly what it is, and we'll see if it is something that's really spooky and weird or not. Mm-hmm. Okay, so I'm just going to give this disclaimer, which I am happy to give frequently. I am not a physicist, so no one get mad at me if I get this wrong. But when I think about superposition from the physics perspective, my understanding is that if you have something like a quantum particle, last time we were talking about qubits, so that's like some kind of small quantum object like an electron that if you were to measure it, which for the record, again, that's a whole nother conversation. Like, what does it mean to measure something? But if you were to quote unquote look at this electron or this quantum particle, you will see that it has some things that it could be doing. And those things have names. Like, I don't remember now, but maybe we talked about last time the spin of an electron. So this is a typical example. Electrons have property called spin, and it can either be in one of two states, to use the word that you said. So either it looks like it's spinning, spin up, or spin down, or like it's spinning clockwise or counterclockwise. Now those are the possibilities that you may find this little electron doing when you quote unquote look at it, or when you measure it, or when you just poke it and say, hey, little guy, what are you doing? But as far as I understand, in physics, and this is where it gets a little bit head scratchy, is what was the electron doing before you looked at it? before you poked it, before you were like, hey, little guy, what are you doing? So it turns out that when you do this measurement or this little experiment or this little prodding, the answer will be one of those two things, spin up or spin down, with a certain probability. Okay, and this particle may have an affinity towards one of these states over to the other. Okay, so it's maybe, I don't know if this is a good example, but it's like if you are a very grumpy person, you were just like born a cantankerous baby. Okay. And someone is like, hey, person, like, here's some good news. Since you are like naturally a cantankerous person, not you, but this hypothetical cantankerous person, they may likely, like more likely than not, respond in like, a negative, grumpy way. So they have a tendency to do this, and that's just their property. So, maybe like with 70% probability, they will reply to you in like some unhappy, grumpy way. And then with 30% probability, they'll be like, oh yeah, that is cool, So there's like this property that describes this thing. So it's kind of like that with, electrons or other particles. With a certain property, when you measure it, then you may find that it's doing one thing as opposed to another. So if you look at all of the possible things that it could be doing, and you sort of keep track of the different probabilities associated to each possible outcome, that array of probabilities, folks call that a superposition. So you say, oh, my quantum particle is in a superposition of these different outcomes together with these probabilities. So it's kind of like the layers of Earth example. Mm-hmm. It's like each layer of Earth is a certain distance from the core of the Earth. Like some are closer to the core and others are farther and farther away. So if you were to have like an Excel spreadsheet, in one column you listed the different names of the layers, and then next to each layer you put like how far away it is from the center. That array together with numbers is like a superposition. You would say, the layers of the Earth are in the following superposition of distances or something.
Mm-hmm. Yeah.
But when you have probabilities, now it's kind of like, because it's random, it's kind of random. Oh, every time I like poke this electron, it could be this or it could be that. I don't know until I measure it. Because there's that inherent randomness, I think that's where it starts to feel less familiar. And a little bit like, my feet don't feel on solid ground anymore.
Yeah, no, I think that hits it. It's that randomness that I want to talk about in a second. But I think you're onto something that's resonating with me around this like meaning of the word superposition in these other contexts. And maybe can we think about it in this context that you just laid out of like probabilistic measurements or probability of an electron being in a certain state or something like that, spin up or spin down. And in my brain, I'm thinking of like, we can measure things a whole bunch of times, like you mentioned, and we could build like a graph, like a histogram or something like that has the distribution of those probabilities. Yeah, and exactly. Then when we talk about the superposition, this like the singular word superposition is describing all of the data that we're observing in that probabilistic histogram distribution. So we can say the electron is in superposition, and that word is describing the possible outcomes of measuring it.
Yeah.
Does that feel about right?
That's great. I love that. And in fact, just to make it even more concrete, it's almost like instead of saying, here's a histogram, you just say, here's a superposition. Like superposition is the physicist's histogram.
Yeah.
Or maybe they're kind of interchangeable. Like they're representing the same concept. You have an array of possibilities and you call that totality or that single collection of arrays of possibilities a superposition or a histogram maybe.
Yeah, no, I like that. And the whole super part just means that it's kind of like one singular word. So maybe this is even just like an artifact of convention of language, one singular word that sits above all of these possible positions. And position is, we're using kind of like in a fuzzy thing because it's like the position on the histogram or the position of the distribution. And that distribution could be actual positions, but it could also be other attributes like you mentioned, like the spin. Is it spin up, spin down, clockwise, counterclockwise? So this superposition like sits above, like the singular superposition sits above this multiple optionality of this distribution of probabilities. That's what's coming
almost
together in my head.
Almost like it's the umbrella term that covers all of these little options in between. So that's the sense in which it's above. I don't know. I like
it. It's like instead of a cape, it's an umbrella.
Exactly. Exactly. This is good. This is good to remember. Okay, all right, our superheroes now come with umbrellas. Okay. Well, this was helpful. Exactly. There you go. So this was good, I think. Neither of us are physicists, though. So maybe it could be helpful if we check in with a real, live, friendly neighborhood physicist and see what they think.
Yeah, I think that's a good idea, because the one thing we didn't touch on was the randomness piece of all of this.
Exactly.
Like, how do you get a distribution? And that, to me, is like the crux of the thing that's hard to understand.
Yeah,
and honestly,
absolutely.
There are some aspects that when you're reading popular culture and stuff, almost take like a religious stance or some kind of religiosity stance of it, of like, well, it's actual randomness, but it's not randomness in the way that we're used to thinking about randomness. And it can feel very, like you said, spooky before, or just like something that is not possible to understand. But I think that that's not the case, but I think we're reaching kind of the limit of what we might be able to do. So I think we're lucky enough today to be joined by Stefan Leichenauer, the VP of Engineering at SandboxAQ. And we grabbed him, and we're going to bring him in now to talk a little bit more about superposition. Welcome, Stefan.
All right, thank you for having me. Happy to be here.
Oh, it's great to have you here, a real expert in physics and all things quantum. Tai-Danae and I have been wrestling with the idea of superposition for this episode. In the previous episode, we were talking about bits and qubits, and we wanted to invite you here to help us wrap our mind around this very different concept. So I wonder if you could walk us through a little bit of how you started thinking about superposition back in the day when you were first learning about the concept.
Yeah, I mean, that's a good question. Superposition and quantum mechanics in general are, concepts that we're not really used to thinking about, as people, experiencing the world. The ideas of quantum mechanics, including superposition, are not that complicated, but they're the kind of thing that a person wouldn't just guess or come up with on their own. These are things which, arose because there's a lot of data in the world that doesn't have an explanation outside of quantum mechanics, and people have tried for a long time to try and understand that data, come up with some explanation that matches everything that we happen to see through experiment. And it's hard to say. I mean, the whole edifice of quantum mechanics, including all the bits and pieces of it, like superposition and other things, all comes together to match all the data. And so it's hard to take bits and pieces and say, okay, this piece I'm going to understand by itself, this piece I'm going to understand by itself, and so on. You kind of need to figure out the whole web of ideas. So to answer your question, the way that I came to understand superposition was through, over actually a long period of time, by thinking about it from many different angles in the context of other things, and then revisiting the idea over and over again. If I think about the first ways I thought about superposition, probably because, if I go back to, say, college, probably because I'm, relatively mathematically minded individual, my, first thinking about superposition just came from the math, right? I learned the math of superposition. I learned the rules of superposition and how to use those rules, and understood it as a mathematical concept. And then over time, maybe filling in the rest of it later. But that's how it worked for somebody with my background. Somebody else might come in from a different angle. Eventually, the whole web needs to be filled in.
Yeah, thanks. That makes a lot of sense. And you're in good company here. We talk a lot about how Tai-Danae is a mathematician and takes a mathematical approach. So I think the two of you could have a lot to talk about when it comes to that. So what I'm kind of hearing from you, Stefan, is that that it's more about learning about all these different aspects of quantum mechanics and quantum mechanics that then leads into an understanding of quantum technology. And that as you learn these different pieces, as they come together, you kind of have this emergent understanding of how it all works. So it might be kind of tricky to just excise one piece of it at a time and be like, okay, here's superposition. And then like, oh, by the way, here's something else like entanglement or something like that. So is that kind of like an accurate?
Yeah.
Okay.
No, I think that's how I think about it. And to be honest, this is also how I think about most ideas in the world. But it just so happens that with quantum mechanics in particular, because it's not something that matches up super well with most people's everyday experience, the way to learn it is to kind of dive in, sort of trust it a bit. Learn however much you can, and then go back and revisit some of the ideas over time. You know, what I would not recommend is picking one thing like superposition, which, you know, of course we're going to talk about and do our best today, but pick one thing and get hung up on it and demand of yourself that you understand it fully before trying to learn something else.
So I think that's a great idea. Also, I just want to say for the record, I think that's a good way to read math papers too. Like if you try to understand each sentence one at a time, you'll probably never finish the paper, or it'll take you a long time. Usually I like to read the end first, the conclusion first, and then go back and read everything. So you kind of like go from here to here to here to here to get this holistic understanding. But however, not everyone listening is a mathematician or has, you know, like the benefit of decades or whatever, you know, in this field of math and physics. Stefan, like you, superposition seems almost, I don't want to say trivial, but it seems very easy and very straightforward from a mathematical perspective. It's like you just say it and you're done, next topic. However, I have noticed when you try to explain that to non-math folks, it's kind of like, okay, you're explaining this. Oh, hi, Adam. Yeah. So I'm speaking we have some experience here, Adam. Yes. So it's a little bit difficult though, when you try to explain a new topic called superposition by introducing another new topic called linear algebra or whatever. And so it just kind of compounds the issue. Yeah. So this is maybe a challenging question, but how might you explain superposition to someone who has never heard of it before, doesn't have a lot of familiarity with the quantum world, and also doesn't have familiarity with linear algebra or, you know, advanced mathematics?
Yeah. So I think the way forward is to talk about what is the data that we see, which tells us that we need something, right? And it's very hard, actually, to draw a super direct line from one, say, experiment and say, oh, this shows there must be a thing called superposition. But we can, without too much trouble, illustrate some aspects of the data which are taken care of. But, you know, we can talk about the different jobs that superposition does for us. What is superposition doing? What is it offering us that we see in the data that is explained by superposition, or that superposition plays a big role in explaining? So I think by talking about some of what we see in the world, different aspects of quantum phenomena that are actually observed, and then we can discuss how superposition helps explain those phenomena. And of course, you could then, if you wanted to, say, well, is there another way to explain those phenomena without using superposition or without using quantum mechanics in general? And depending on how deep you want to go, that can be a very difficult question. But there have been, you know, for the last 100 years, people have tried very hard to explain all the different things that we see in the world without using quantum mechanics, and it has not worked. So, and that's, you know, that's good enough for me.
Yeah, I think that sounds like probably the level of depth that we need to get to here, or even that's probably a lot deeper than we need to get to here. But yeah, so maybe we can start out with some of that data, Stefan, or the phenomenon that this idea of superposition has come into play to try to explain pieces of data.
Right. So something that people often hear about quantum mechanics, which is deeply connected with the principle of superposition, is the idea that measurement outcomes in quantum mechanics are not completely precisely determined from the outset when you do the measurement. Sometimes they are, but sometimes when you do a measurement or you observe something, you take a look at some aspect of a particle or an object, you want to see which direction it's pointing or what color it is or something like that. The answer that you get maybe is random. Like you might repeat the experiment many times with exactly the same setup, and you get a different answer each time. And you can make a histogram of all of the answers that you get and collect statistics about, how often you get one answer versus another, how often the thing is red versus blue, or the thing is pointing up versus pointing down, or different kinds of things like that. And the thing that quantum mechanics predicts for you is the histogram, not the outcome of any individual experiment, but it will tell you the probabilities for different things to happen. And so there's this randomness inside of quantum mechanics, this inherent randomness. And superposition has to do with how we think about describing that randomness in our mathematical description of the world. We use the concept of superposition to take into account that randomness. This is one of the jobs of superposition. But of course, it's not the entire story.
And that's a lot different than what's happening outside of quantum mechanics, like that histogram thing, or checking if there's a color or not a color.
That's
You're
right.
talking about
That's
like
right.
determined or predetermined outcomes, things like that. Can you talk about that just for a little bit of the contrasting those types of observations in quantum mechanics versus in other contexts?
That's right. That's right. So it may not seem, the fact that some things cannot be predicted is, depending on, how you're thinking about it, may not seem totally crazy, right? There's lots of things in the world which appear random, which I cannot predict. Good luck trying to predict the weather, especially more than a week or two out. It's very challenging, and in many ways it seems random, especially in detail. Exactly when will it rain, down to the second. Very hard to predict, essentially impossible to predict. But is that a quantum thing? No, not really. What that is it's just we as, limited humans, or, the computers that are doing our calculations for us, can't keep track of everything that's happening in the world. So we don't have all of the information. And that means, because there's some things we don't know, the particular outcomes cannot be precisely predicted, just because we have incomplete information about the world. That's kind of a usual way in which we think about probability and randomness in nature that we observe. It has to do with missing information. In quantum mechanics, it's different. In quantum mechanics, there is fundamental uncertainty. The most you can ever know about something is contained in what's called the quantum state of the system or of the object. We say, all right, we know everything that we could ever possibly know, even in principle, and still there's some randomness when we go in and try to make a measurement. And that essential quantum randomness that comes from fundamental uncertainty that has nothing to do with missing information, that's the kind of randomness which is captured by superposition.
Interesting. So, go ahead, Tai-Danae.
Okay, well, I was just going to jump in and ask maybe a question for the benefit of the audience. Some folks may have heard, maybe through pop sci articles or, social media or something, that superposition is often connected with this phrase, both at the same time, or like somehow particles are doing two things at the same time or in two places at the same time. Can you explicitly make the connection between that phrase that folks may hear in popular media versus what you just said?
Yeah. So I'm really not a fan of those kinds of phrases.
Yeah.
Those kinds of phrases are, it's an attempt to use some, to try and capture what you mean by quantum randomness or superposition in a single sentence that tries to communicate it very quickly.
Yeah.
The truth is, there's a little more to the concept than that, and it takes more than just one sentence to explain it. And the danger of these one sentence explanations is that people get the wrong idea. Mm-hmm. And so both at the same time, or any kind of sentence like that does not capture the idea. Really, saying that the quantum state contains a superposition, so quantum state meaning everything we could, our maximally informative description of the reality contains a little bit of randomness, which means there is a superposition in there, a superposition of, say, different measurement outcomes. Saying that does not mean, it's both at the same time, or it's, it's actually, it's neither. You cannot even say it's this or this. It's just a new kind of, situation that the system can be in. That is not, there is no other description of it. There is no other set of words to use besides its superposition. And then the best we can do is, say what we mean by that by telling you what the rules are for, what do you see when you do this, when you look and you say that the quantum state had superposition or was in superposition. But saying that it's both at the same time or something like that is fairly misleading, in my opinion.
Okay, so that's helpful, Stefan. Thank you for making that connection between the sort of randomness aspect and then also what people hear in, popular media. But now that we have a little bit of the conceptual understanding, I think it would be nice to have a concrete example. So earlier you mentioned kind of like what do we observe in the lab with our eyes, so to speak. Can you give us an example to, drive this point home?
Yeah. No, definitely. I think, thinking about one or two examples is definitely the thing to do now. Part of the trouble in discussing quantum mechanics is that many of the most interesting and exciting examples are not the kinds of things people have experience with. So that makes it challenging. But there are a couple that, at least most people see some glimmer of these examples, even if they may not understand what they're being told at the time. But we can discuss them, a little more depth right now. So one example that I think people see a lot, and a lot of people learn it in school, is the idea of the so-called electron cloud around an atom. So we learn in school early on that there's this naive picture of an atom where you've got the nucleus, protons and neutrons at the center. And then outside of that, it looks kind of like the solar system. There's electrons that orbit the nucleus, and sometimes people draw pictures showing these electrons orbiting in the same way that planets orbit the sun. But then we learn that that's not correct. And in fact, the dawn of quantum mechanics in some way was thinking about that picture and why it was not correct and what the correct picture actually is. And so what we learn is that, the correct picture does not have these electrons orbiting the atom like those planets orbit the sun. In fact, they're more like a cloud around the atom. That there's this diffuse, if you see pictures of it, cartoon images of it, artist depictions, it's this diffuse, fog almost around the nucleus. And it's supposed to represent the electron cloud. What in the world is the electron cloud? What does that mean? Well, really, that's a kind of an artist's picture of a superposition. So the electron does not have a definite position. I would not say that it's in all those positions at the same time, of course, as we just discussed. It, in fact, does not have a definite position. But if we were to try and see where it was, if we were trying to measure its position, we would get a random outcome. And the random outcome would be somewhere in that cloud. And the more dense parts of the cloud, if you looked at it like it was fog and it had, some parts of it, say, close to the nucleus usually, are a little more dense. The dense parts of the fog represent areas where you're more likely to see the electron if you were to look for it. And so electrons in atoms, in these sort of atomic orbitals, as they're called, these electron clouds really represent the fact that the electron state is a superposition over all these different locations that the electron could be found. And that's the natural kind of situation to find an electron in an atom.
Okay, can I just ask a follow-up question then? Since this example has to do with position, is this kind of where the word comes from? I mean, I'm just asking a naive question. It's not that it has a position, but it's like some superhuman. No. Can you explain the etymology behind this word superposition, and does that relate to your example?
I actually don't know the etymology of superposition, but I think it's much older than this example, than even quantum mechanics. I suspect that people were using the word superposition like long ago in the, certainly in the 1800s to describe, say in when people are studying like electromagnetism, for example, and they talk about electric fields and things like that. You learn that the electric field also satisfies a property called superposition. And this has to do with the fact that, the equations are linear equations. And so if you take two solutions to the equation and add them together, you get another solution to the equation. So the fact that you can add things and add two solutions and get a new solution, people often call that superposition. I don't know if they were using the word superposition to describe that phenomenon in the 1800s, but they certainly knew about that phenomenon in the 1800s. But it's an interesting question.
Yeah. All right.
That's very interesting. And mathy. So that's always good for at least 2/3 of us here on this particular podcast. But Stefan, I'm a biologist, so definitely chemistry is in my blood, and the visuals that you're putting into my head talking about the electron cloud resonate like very clearly. Using this information of superposition, though, like my question is, yes, there's the superposition is like kind of a natural state or phenomenon of the electron. But I'm trying to think, like, where is it? Like, where is the electron? Like, is it really diffuse over all of these things? Is it still an electron? Or are we kind of changing the way that we're thinking about an electron? Is it being spread in this fog? Like, how do I connect the fog to the actual physical thing of an electron and where it is in its orbit or its fogginess?
Yeah, no, that's a really good question. And it's a very deep question, in fact. So, and this is part of what makes quantum mechanics difficult to think about until you get used to it. So let's leave quantum mechanics behind for a second and think about how we are used to describing the world. As say, we'll put on our physicist hat, but we'll put on our pre-quantum physics hat. We say the world is filled with molecules or particles or whatever that have positions and velocities. And we can try and some kind of billiard ball model where they're, moving around. They have positions, they have velocities, they knock into each other and things like that. And basically, if we wanted to look at the molecules, we can describe them mathematically, say, or we can talk about where they are. If we were to look at them, their positions would be the positions that our equations say that they're in, that kind of thing. And so the way that we talk about the world pre-quantum is we talk about the way the objects in the world are configured in what they're actually doing, right? And then the thought of looking at them and actually performing the measurement and seeing where they are is kind of an afterthought. Well, of course, they're where we say they are. If you were to look, that's where you would find them. In quantum mechanics, it's very important to realize there's like an extra layer in there which you can't ignore, which is that there's a difference between what the thing is actually doing and your measurement of the thing. So the question that needs to have an answer is, where will I see the electron if I choose to measure its location? If I choose to look for it, where will I see it? And of course, the answer to that is given by, there is no definite answer in the case we were just talking about. There's a probability distribution over where it might be, and that's this cloud thing. If you don't look at it, And you try to ask a different question, which is, where is the electron just in itself? Forget about me trying to measure where it is. Just tell me where it is, in the same way that you told me about where the billiard balls were in the pre-quantum world. Those kinds of questions cannot be asked or answered. The only thing you can do is talk about where the electron is when it's looked at. So, unfortunately, the question of where is the electron doesn't really have an answer, independent of the measuring of its location. And this is a thing we have to get used to in quantum mechanics. This is part of why I say I don't like the language of, well, it's everywhere at once, or it's really the question of where it is doesn't have an answer. The only question that has an answer is, where am I, say, likely to find it if I were to look for it?
And that's a property of the quantum world, is what I'm hearing you say.
That is a property of the quantum world.
And that more information isn't going to help us. That's just baked into the system. Is that right?
That's right. That's right. The information about where, you might have thought there was information that just said where the electron is. But what quantum mechanics says is that there is no such missing information. It just, the question just doesn't have an answer. The only question that has an answer is, where might we find it if we were to look for it?
One of the things that was difficult for me when I was first learning this stuff, or the first time I heard these ideas, it was actually sort of easy for me to be like, okay, I can buy that. I mean, there are a lot of things in the world that I don't understand. So I guess this physicist knows more than me. That's fine. But then I didn't really understand it, because I don't know what it means to measure the position of electron. Like you just said those words and I'm nodding my head. But actually, just to make this super concrete, because I don't look at electrons, like in my free time. So what is a concrete example of how a person can definitively measure where an electron is? Is this like shooting it with a laser, or what? Can you give an example?
Yeah. I mean, that's a good question. The answer is, well, you could try to measure it the same way, and measure its location the same way you measure other things' locations, which is to bounce light off of it. So how do you know where, your coffee mug is? How do you measure its location? Well, there's light bouncing off of the coffee mug, and then that light is caught by your eye, and your eye, some kind of chemical reaction happens that eventually gets some signal into your brain, etc. But it starts with light bouncing off the coffee mug. And so you can try to do the same thing to measure the position of the electron. Now, the difference between the electron and the coffee mug is that you don't really have to try to set up a situation where the coffee mug has light bouncing off it that is, giving you information about where it's located. It just kind of happens naturally. That's why we don't notice anything quantum about the coffee mug. And in fact, the reason why the electron likes to sit in these superpositions of atomic orbitals is that, well, it's not every day that a ray of light comes in and hits the electron in such a way that it's able to determine the electron's position. So to go in a little bit more detail, add a little bit more physics into that, in order to say where something is, using, say, a beam of light or a photon or something, in order to, say, determine the position of an object within some, accuracy, within some window of accuracy, you need to be using light which has wavelengths smaller than the accuracy that you're interested in. And atoms are really, really small. So in order to determine the location of an electron at a level of accuracy that's really small compared to the size of the atom, you need to be using wavelengths of light that are that size or smaller. And those kinds of things, they're just not bouncing around everywhere. You can try to shoot these things, X-rays or something, at an electron, and you can succeed, but you have to try, and then you have to detect those things. But this is kind of how you would do it. and it would, it's a detailed kind of experiment to do, but that's the idea.
That's interesting. And then I think we won't get into this here, but by doing something like that, you're influencing other attributes of that electron. So you may be measuring its position, but then by doing that measurement, you're actually changing other conditions or other attributes of the electron, which is a whole other ball of wax. So if I can, Stefan, I think that we started off this part of the conversation talking about how superposition can explain certain observations in data and randomness that is present. I'm going to say naturally, but just is present in its regular state in some data sets that are quantum. What other types of observations or phenomenon can superposition explain that can't be explained away using things like classical physics?
Yeah, no, it's a good question. So I think I said before that one of the jobs of superposition was to account for this randomness that we see. If all there was randomness, well, you might be suspicious that I needed something as sophisticated as superposition to describe it. Like we might just use the usual non-quantum language we use to talk about probabilities all the time. We just, maybe there's some fundamental probability, but that's okay. There's just probability. Superposition adds a little bit more. So what else does it add? Or what else is involved in this quantum states and quantum randomness that is not there in other kinds of randomness? So the electron in the atomic orbital, the electron cloud, is actually a good example to illustrate this concept. So if you consider like an electron sitting in an atomic orbital, say the orbital of lowest energy, this is maybe something that people have heard, some kind of other words that people say at the same time as they're saying electron cloud. They talk about things like ground state. What is the ground state? What do these things mean? Basically, what's happening there is this superposition over different locations that the electron can be in. It's random when it comes to measuring position, but if you were to measure another aspect of the electron's say state of being, you would find answers that are not random at all. Some things are random, but some things are not. In this case, the energy of the electron is not random. These atomic orbitals are determined precisely by saying what kinds of states can the electron be in that have definite values of the energy that are not random. And so having a quantum state, which if you were to measure the position or the location of the electron, you get some random thing. But if you measure some other aspect, say the energy or the angular momentum, or other things which are important for chemistry, you'd find definite values. You would not find randomness. So having some things be random and some things not be random, that would be very challenging to mock up some non-quantum explanation for that kind of behavior. But it is perfectly accounted for using superposition.
Can I ask a math question about that?
Yeah.
Does that mean that the state of that electron in terms of linear algebra looks like a linear combination of its different position possibilities, close parentheses, tensor the one energy state that it could be in?
No. So that's not what I'm saying.
Okay.
What it actually is you've got the states of the electron in terms of, say, using linear algebra language. You could describe the electron in terms of the position basis, meaning you can say that the state is a linear combination of being at different definite positions. Alternatively, you could describe the state of the electron in terms of the energy basis. Mm-hmm. The electron is in a superposition of different possible energies. Mm-hmm. And these are two different bases, and you can express one of them in terms of the other. Mm-hmm. So what I'm saying is the state of definite energy can be written as a linear combination of states of different position. And that's what these atomic orbitals are. They are a state of definite energy and angular momentum. And then if you were to express those in terms of position, you would find that you have to use a linear combination of different positions.
Got it. Thank you.
Yeah, that's very interesting. I'm going to try to unpack that later, probably on my own, or maybe over lunch with Tai-Danae. But that's really interesting. Stefan, if I can, I want to take us in a slightly different direction for the last part of our time with you. I used to be a research scientist and focused on basic research. So all the things that you're talking about with basically creating formulas, creating theories to explain phenomenon around us or to explain patterns in the data resonates like super deeply with me. Mm-hmm. But I'm also interested, and I think some of our viewers might be interested in the application pieces of something like superposition. So we've talked a little bit about how this is a real phenomenon that can be observed in lots of different sort of contexts, and we talked about one context in particular. But how can we, as quantum information scientists and engineers and companies and whatnot, how can we take advantage of a property like superposition to create things that can better humanity, for example?
Yeah. I mean, it's a reasonable question. I mean, the fact is that superposition is it's in some ways it is the property that quantum mechanics has that just the classical world doesn't have. So, and it encapsulates many things inside of it, including, the things that we've discussed. So any kind of quantum technology in some way is going to be taking advantage of superposition. In fact, many technologies that already exist take advantage of superposition. So things like lasers, for example, take advantage of superposition. But anything like a quantum computer, for instance, takes advantage of superposition in a deep way. Especially this aspect we were just talking about, where maybe in terms of the energy, the state might appear not to be in a superposition, but the same state, when looked at in terms of location, does appear to be in a superposition. This kind of idea of looking at it from the point of view of two different things you might observe, and having it be in a superposition with respect to one and not a superposition with respect to another, that is used over and over and over again in the creation of quantum algorithms for quantum computers. Another way that superposition is extremely important is in anything involving entanglement. So entanglement is another one of these key words, and you can't have entanglement without superposition. It kind of comes with the territory. And so there are all kinds of interesting communication protocols, say, that make use of entanglement over long distances, and those are using superposition in a very deep way. So it's a very fundamental kind of concept, and I would actually hate to create the impression that it's so exotic that only new quantum technologies are taking advantage of it, right? Really, all of the modern understanding of chemistry relies on it in a deep way, et cetera, et cetera. So it's there, and it's here to stay.
Oh, that's definitely an important reminder. Tai-Danae, do you have any last questions for Stefan before we give him some time to have some parting thoughts for us?
No, I think that was great. This was really helpful, Stefan. Thank you for diving deep and answering all of our questions on this topic. We really appreciate it.
Yeah, well, I had a lot of fun. Yeah. Maybe I can come back and do another one time.
I think that you were just teasing entanglement. So I think that that's probably a nice, obvious spot for us to have you back to talk more about entanglement. Is there anything else, Stefan, that you'd like to leave with viewers who probably just learned more about superposition than they've ever heard before? I think that it's a really great reminder how you ended a moment ago, that this is not some like newfangled thing that's just coming out now. So it's part of a fundamental part of chemistry, and now it's just being applied potentially to other things. Any other kind of words of wisdom that you'd like to leave folks with?
Yeah, I guess I'll just call back to what I opened with, which is that, what we discussed today, superposition, and really only some of the aspects of superposition, is one little piece of a vast web of ideas, called quantum mechanics. And there are many other, examples you can look at, many other data points you can try to assimilate into your understanding, and many other concepts besides superposition that go into that arise in quantum mechanics. And these things are all connected. It's hard to talk about them in isolation. And so this could have been a good starting point for many people, and I would encourage those people to go try to get more information, maybe go into the more mathy side, maybe do something else. For those people for whom this was not their first time hearing about superposition, it's not the first, node on this web of ideas. Don't stop what you were, keep going, keep learning more stuff, but also go back maybe to the first time you heard about superposition, maybe with a new context, and, try to synthesize some of the things we talked about today, maybe that were new, and, get them squared away with things that were already in your head. And this kind of process is really it's kind of how you learn anything, but especially something like quantum mechanics.
That's great advice.
Definitely great advice. And hopefully folks will stick with us throughout this series as we try to build up those pieces one by one, and then have that recursion of encouraging people to go back, listen again. And I'm sure we'll have future episodes that also touch on superposition again, in combination with other phenomenon. But I could see us coming back and just revisiting superposition in a couple of months, given what we'll talk about between now and then. So thank you so much, Stefan. It was great to have you here, and thanks for already offering to come back. We will definitely take advantage of that.
Yep.
Super.
Thank you.
Thanks.
All right. I thought that was great. I'm so glad that we had a chance to bring Stefan on board. Adam, before we wrap up, any closing thoughts from you today?
Thanks, Tai-Danae. Yeah, I thought that was very informative. I know I learned a lot there. Yeah. One thing I want to say is that a lot of times things can seem simple for folks that are learning things maybe for the second or third time. And I think we talked about that a little bit during the section of the show with Stefan, that superposition actually seems simple from a mathematical perspective, for instance. And I want to stress another point that Stefan made, in that this is a long journey of understanding these concepts. And it's very understandable if things do not feel that simple from the get-go. They weren't for me, for example, and they still aren't in a lot of cases. Even with superposition, I'm still working to wrap my mind around really what it means and what the implications are and applications could be, and all of those things. So I think that it's totally understandable if you got lost a little bit during parts of that conversation. Leave a comment below if there's something that we can specifically address. But the good news is that you're here. You're maybe even still here at the end of this episode, and stick with us. Stick with it, meaning stick with your learning journey on quantum physics, quantum mechanics, and all things quantum technology. We're here for you. We're going to be on this journey together. So stick with that journey. Stick with us, and we're going to keep on talking about these concepts. And we'll circle back to superposition and some of these other concepts after we build a little bit more foundational knowledge. And I think you might surprise yourself if you're still scratching your head a little bit. You're in good company, and I think you'll be scratching your head a little bit less and be excited to talk with your friends and family about these concepts a little bit more as we kind of move on to other topics and then circle back around. What do you think, Tai-Danae?
I think that's great. As you were speaking, I'm thinking things are easy when you understand them. But getting to the place where you actually understand them is not so easy. So yes, as you mentioned, this is all part of a learning process. And we're so glad that folks have tuned in so far. As you mentioned, keep on listening, and we will see y'all next time.
See you then. Bye.